Hello, everyone, and thank you for tuning into this presentation. My name is Kasra Yazdani, and I'm a PhD student at the University of Florida. Today, I will be presenting on error bounds and guidelines for privacy calibration in differentially private Kalman filtering. Multi-agent systems naturally arise in a variety of settings. For example, the trend in machine learning right now is to use more training data and bigger models that require processing the data over a network of GPUs. Or in autonomous systems, the vehicles communicate their locations and their velocity data to let others in the road know of their presence. Or in smart power grids, we are constantly sharing our power consumption data with the network and utility companies. Well, this sharing and exchanging information enables a network of agents to be able to work with each other. At the same time, this information that is being shared might be rather sensitive. I'm going to a couple of examples to illustrate this. For example, in a power consumption or in a smart power grid, the power consumption data can expose one's daily activities. For example, if you turn on your coffee machine when you wake up, let's say at 8 a.m., well, the power company knows that you just woke up. We mentioned that distributed and multi-agent systems have emerged across a wide variety of applications. In some of these networks, the cloud is the recipient of the data. Sharing information naturally leads to privacy concerns, and therefore it is really necessary to preserve the privacy of individuals, although their information must remain useful for the analysis and decision making. In this paper, we focus on linking control theory measures with privacy of systems, and we carefully quantify the impacts of privacy upon systems. So we are going to first talk about what we mean by privacy. So what we'd like to be able to do is to utilize the data while at the same time protect the privacy of the individual. So what do we mean by that? Let me ask, how many people have sent happy face emojis in Denver today? The answer to this question is not reflective of a person who sent an emoji. It is reflective of a whole population. And let me ask, how many happy face emojis did Joe send today? The answer to this question is influenced by only one person's data, Joe's data. So what we'd like to be able to do with data privacy is to allow queries on the left whose answers reflect a trend on a population and disallow queries on the right that reflect properties of a specific individual. This task is particularly challenging because if an individual decides to not share any information, then there is no data to be utilized. And if they share data, their privacy can be compromised. So there's always a trade-off between privacy and utility. Sometimes we want to reveal information, but protect it from the recipients simultaneously. In this sense, there is a bit of a paradox here in that we're trying to share information without oversharing. Now I want to give you an example of how this form of privacy has come up before. Organizations are currently sharing their data with either the public or other organizations, and the risk is that the organizations may share more than what they intended to share. So it may be possible to go from the data that seems to be safe back to the identities of the people in that data set. So what do we do to solve this problem? Today, what people do is anonymization. If you take the names out of the data set, then you can't figure out who is in the data set. Anonymization, though, has a couple of big problems. It limits utility. So if you take out identifying information out of a data set, then there is less data. But perhaps the bigger problem is that it doesn't solve the problem of data privacy, really. Anonymized data are subject to re-identification attacks where you link the anonymized data with another data that has identifying information, and you can recover the identities of the people in the anonymized data set. There are a lot of examples of this. Perhaps the most famous one and my favorite one is the Netflix Grand Prize Challenge, where the researchers were able to use IMDb data, which is another movie rating company, and recovered identifying information about Netflix customers. So the question is, how can we do this? How can we share without oversharing? As we go forward, privacy must address these challenges. To do this, we're going to use differential privacy. If you have an iPhone or have recently taken an Uber, you are already using this technology. Differential privacy is not a procedure. It is a definition of what privacy means. So differential privacy gives you a definition of what it means to have privacy, and then you can design algorithms, which we call mechanisms that you can prove give you this property. And it has a couple of really nice properties. For example, it is robust to site information and it is immune to post-processing. And what we mean by that is that any post-computation that you do on a data that's already privatized by differential privacy, then it is going to remain private. And we are going to touch upon this point down the presentation. In here, we formally define differential privacy. The output of a differentially private mechanism makes two adjacent trajectories, x and x prime, produce similar outputs. The degree of this similarity is tuned by privacy parameters epsilon and delta, as we can see in the definition. And we are going to formally define what we mean by adjacency in just a second. So I'm going to give you an intuition of what differential privacy actually gives you. Imagine you have an analyst who is posing a query on a database and they get an answer. In this case, the adversary is trying to figure out something about an individual. Now imagine you have a second data set that is identical to the first one. The only difference is my data. So the first one does not have my data, but the second one does. If we were imposing the same query on both data sets and get two different results, the differential privacy says that these two answers have to be very, very close to equal. Therefore, what it means for me as a person who's deciding whether or not to contribute my data is if the answers are very close to each other, the analyst or the adversary can't tell which data set was used to run the query. If the analyst can't tell whether my data was in the database or not, then I'm going to receive the same outcome. And the analyst is going to make the same decision whether or not I contribute my data. This is what we want from privacy. We want to make sure bad stuff won't happen to us because we contribute our data. Formally here, I'm going to define adjacency. We fix a parameter, privacy parameter B. And as we said, we are going to take a look at differential privacy for systems. And as a result, we define the adjacency for trajectories. The trajectory is whose L2 norm or the difference between the L2 norm of two signals or two trajectories x and x prime are within a ball of radius b are called adjacent. It is the role of the mechanism to approximate query outputs, which are statistically close to each other, determined by privacy parameters epsilon and delta, as we mentioned. In this work, we are going to use differential privacy for trajectories, which are made private in the form of a stochastic process. We assume a discrete time linear dynamic system with process noise W, and the output is denoted by Y. I'm going to mention that our results are easily applicable to a network of agents, although we are going to focus on only one agent for the sake of simplicity of this presentation. The Gaussian privacy noise is added to the output of the system before sharing it at each point in time or at each gate. Epsilon and delta, as we mentioned, they are tuning parameters. The parameter delta represents the probability of the privacy failing, so we want that to be very low. And in general, smaller values of both parameters, epsilon and delta, mean that we are more private. Well, we just added noise to our system, and introducing this type of noise or privacy parameters naturally involves sacrificing a level of accuracy. And in this work, we are going to really focus on to study the trade-offs and effects of privacy on the performance of our system in a rigorous manner. Oops. We mentioned that adding noise affects the performance of our system. And as a result of the added noise, the cloud is not going to be able to estimate the state of the system really accurately. Therefore, the cloud receives the privatized outputs of individual agents and runs a Kalman filter on the privatized outputs. So the natural question that just comes to mind is that, well, is this allowed? And the answer is yes, it is post-processing. Kalman filtering is post-processing, and we already touched on this, that differential privacy is immune to post-processing, and therefore filtering private data is allowed. There are the a priori and the a posteriori update equations for the states of the systems based on the normal Kalman filter, and the error covariances are given below. So the question is that we want to ask is that how accurate are the cloud estimations given that we added differential privacy or privacy noise to our system? So what we'd like to be able to do is to explicitly quantify the ability of the cloud or any potential recipient of our private data to uncover our agent state trajectories. One natural way of doing it is to look at the mean square error of the prediction and estimation steps of the Kalman filter that is processing the private data. The mean squared error is computed by the trace of sigma and sigma bar. Privacy and utility are inherently conflicting goals in the sense that, well, the greater the level of the privacy it is, the less useful the information will generally be. To investigate this, we also studied differential entropy, which is an information theoretic tool which allowed us to measure the leakage of information, basically. Differential entropy is within a constant factor of the log determinant of the covariances sigma and sigma bar, and we develop bounds on the differential entropy or the log determinant of sigma and sigma bar as well. Okay. Well, without privacy, data transmission could reveal the agent's state trajectory and as a result, compromise agent's privacy. Through bounding the trace of sigma and sigma bar, we can directly relate the control theoretic concerns like mean squared error or filter error to privacy through epsilon and delta, and therefore this allows us to elucidate the fundamental limits of information accuracy when we're dealing with private trajectories. This work has also been extended to a broader problem of linear quadratic control, and that paper is already under review. In the bounds that we can see, there's a lot going on, but I want you to pay attention to the dependency of the bounds upon the privacy through sigma, and the rest of the terms are a bunch of constants. And the sigma is naturally dependent upon epsilon and delta, as we saw earlier. We have additional bounds on the paper on differential entropy as well, but for the sake of brevity of this presentation, I'm going to skip over those results. And picking the right privacy levels, epsilon and delta, is notoriously difficult in practice. We all saw Facebook's data privacy scandal testimony before the US Congress a few years ago, and choosing the right levels of privacy for Facebook users were a big part of the problem there. Using the privacy guidelines that we provide here on epsilon, this enables the people who are not experts in privacy to have the technical and rigorous protections against anyone who is the recipient of these private trajectories, be it the cloud, other agents, the network, or one malicious adversary. And this is the main point of the paper, really, automating how to calibrate privacy. We simulated an agent with the following dynamics, which is a simplified version of a traffic monitoring system. We proceed to enforce input perturbation differential privacy with parameters epsilon and delta, as we can see. The result of the presentation or the simulation are presented below, and we are comparing the actual instantaneous error of the estimation of the agent's states to the average bounds that we have developed. We can see some ephemeral bound violations, which is to be expected because our bounds hold on average. So in summary, this paper provided novel bounds for both filter entropy and filter errors in state estimation. And also, we proposed guidelines for calibration of privacy levels when enforcing differential privacy. And with that, I would like to conclude this talk and hear any questions that you might have. Thank you very much for your attention.